Oh, hi. Yeah, I noticed that a few of you have joined already. That's good. Let's, as always, just give 2 or 3 minutes to see if anyone else joins. So yeah, you can start downloading data and yeah, put in a folder and the whole uh, setup that we always do, right? Working directory, all of that. You can start going through that, and we will start soon. Yeah, just waiting to see if anyone else joins. Okay, I think we will not have anyone else joining us, so we're ready to start. So before we go, oh, it's erasing. Let me put the code share website. Oh, it's there. Where I put the codes that we're going to use today is quite massive, over 470 lines. So make sure you grab everything and just copy, don't cut, as always. So it's available for everyone there. Put it in an R script. Yep. And, keep everything ready while we start. Let me just put my presentation up. I trust that you guys can see my slideshow there. Just wanted to give you a quick heads up that the second quiz will be closed next week, right? Next Tuesday. So make sure you go there, spend the time, and do it before the actual deadline. Deadline is 4 p.m., not midnight, we have moved away from those deadlines. So it's middle of the afternoon, so you guys don't miss it. And report one, assignment one, has been also uploaded to Blackboard. So make sure you guys stop by the assessment folder and assignment one folder, so you get the questions, data, and then you can do it with plenty of time. We have a little bit less than a month for that. So yeah, just another announcement, and is that regarding assignments, we can discuss assignments in consultation sessions. I can give you pointers. I can tell you if your answers are correct or not, and so on, right? To extent. But for the quizzes, I am not, right? I should not be like giving you answers or leading you towards a correct answer. So I would like to ask you kindly to refrain from doing such or making such questions in the consultation, because yeah, these quizzes are meant just for yourselves and for the practice that you guys have on like, you know, reviewing the contents as we go on. And so yeah, make sure that you keep that into account. So the topic that we're going to discuss today is co-integration. With co-integration, we try to determine if there exists a correlation between two or more time series in the long run. So pretty much like you put it in similar in easier terms, it means or we try to determine if they wander following, if not parallel paths, very similar paths, right? This is very valid in the context of forecasting, because having variables that are correlated and some macroeconomic variables are like not easier, but sometimes more likely to be predicted. So if those predictions are okay, then the predictions for like in terms of general behavior for the correlated variables would be very similar, like, right? So it also goes with a little bit of a response in terms of what happens like when a variable is affected by something, then we can also observe that other variables will follow similar situations, if you know what I mean. So it's that's what we're trying to determine. In theory, and like from the approach that we're going to use, the way to determine if two variables are co-integrated is that if we take the difference between them, so one minus the other, the order doesn't really matter, will generate a stationary time series in mean, right? We don't worry about variance for now, but if the difference between two will generate a stationary time series, or for, yeah, for 3 onwards, the residuals from regressing it are stationary as well. We will test how to do this. And remember the procedure. I will try to, like for the first time series, I will refresh the procedure of the Dickey-Fuller test. But from some point onward, I will start assuming that it's clear, because today we're going to do a lot of repetition in the operations. So yeah, I want to make sure that you guys, so if you like are struggling with something regarding the procedure of the ADF, I would like to first ask you to go and double check the recording from last week, and that should be a good refresher there. One condition for a correlation analysis to be valid is that all time series should be integrated in the same order, right? Or yeah, like the wording here is a little bit of a gray area. We usually say that a time series is not distinguishable from an I1 process in case it's integrated order one. But that's like the right wording, but for simplicity, if I'm allowed the term, I will just say integrated in order 1, but that means that it's not distinguishable from an I1 process. Okay, it's sometimes in these things the procedure is important, but also the wording of the conclusion is also important. Like you guys remember when you are doing whatever hypothesis test and you don't say that you accept the null hypothesis, but you word it as you fail to reject, it's kind of a similar situation. You don't uh, uh, like the appropriate conclusion has to be a little bit longer, right? So we will start by that, by looking at the order of integration of the time series that we're going to analyze today, right?
Can I just ask
Yeah,
something? So does I'm just thinking. So you say I0 there.
yeah,
Does that mean before you differentiate it, they both have to be I1? Is that what you're saying?
yeah. The difference has to be I0, but
Oh,
before
okay.
you, is that it's not differencing each variable, but taking one minus the other variable. That's what it means by the difference between two time series.
Oh, okay. Right. Yeah.
Yeah. We don't worry about it. We will practice today. So I hope it will be,
Okay.
it'll be good.
Thanks.
But yeah, before working, they have to, or yeah, they will have to be not I1, but on the same I. So both I2, both I1. Yeah. Okay. So we will start by looking at the order of integration of this time series. So let me display the questionnaire. We're going to work with a time series, with a data set called term structure. In here, we have information regarding 4 measures of interest rates here in Australia. The 5-year and 3-year treasury bond rates. So those are the rates that money is lent in the capital market. And the 180 days and 90-day bank accepted bills. So those are the interest rates that money is lent in the money market. So again, for short, we're going to call these yearly interest rates as capital market interest rates, and the daily interest rates for the money market interest rates. We have monthly data analyzed, so that's not a process that we don't need to discuss. We have information from June 1992 to August 2010, so we have 219 months of observations here. So let's go through each of these variables independently and check the order of integration before we actually do any co-integrating analysis. So I trust that you guys have set up your R, you have all your data there. These packages I think we installed, or we should have installed at least 3 of these 4, if not all 4, but I'm not sure if ATCA has been installed. So if you don't have it, you can install it real quick here on the package tab. Click here on install, and my R is taking a little bit of a time there, or you can do it manually. Actually, with code, it's up here. So you just type the name of the package. Make sure you are consistent with the cases, lowercase, then uppercase on the last 3 letters. And yeah, I'm not going to install it because it's already in my library, so I don't need to do it again. And I always recommend not to do it once you already have it installed. It's very rare that packages in R get updated frequently. So it's good to just keep it once you have it installed, it's good to just keep it there and just activate the packages. So if you must, please run these library commands. It should, like dplyr here, it should activate these packages. Forecast is active. So yeah, you will notice that this little boxes have been ticked. So that means that the packages are good to go. So make sure you run this. I'm not gonna run them. So from last week, you guys probably remember that we did a whole procedure of how to perform the Dickey-Fuller test, right? How to program the Dickey-Fuller equations and all of that. So we came up with this huge equation. What we're going to do is save it as a function called ADF estimate left for levels. So make sure you highlight up to line 51, okay? From line, wait, let me see if code share is consistent to this. We started line 9. Yeah, from line 9 to line 51. Make sure you run them like all at once. Don't like highlight just chunks of it. Make sure you grab the whole thing. And once you run it, as we learned a couple of weeks ago, R will create a function that does all this process and only takes 2 inputs, whatever function we are analyzing. Wait, no, whatever variable and the number of lags in the Dickey-Fuller equations, right? This one will control for all the variations of the Dickey-Fuller equations, whether if they have a constant and no trend, a constant or and a trend, or neither of those. All of that is controlled here, and we will get the AIC and BIC of those Dickey-Fuller equations, as well as the estimates will be stored. Okay, so make sure you run that because we're going to use this function quite a lot. And we did the same, but now for the difference. So in case we don't want to do ADF of Y, but for delta Y. So it's pretty much the same, but it's just now programmed to do for the difference of Y. So you just grab from lines 55 to 101. Make sure again you have selected everything and run, and these 2 functions, diff and left, should be here on your oops, sorry, should be here on your environments. Okay. And now we will start our work. Again, explanations on this code last week, right? It's exactly the same code that we used, but for simplicity, instead of having to copy and paste the code again and again and again, programming as a function allows us to avoid having to do this. Now let's load the data. So you should have that term structure data set in your folder. I have it here. Make sure you use the read.delim command with CSV extension, and that you keep the header as true. And I think you need to add the separation, but not 100% sure, but just put it there just in case. So R will read the data here in an object called my data. So we have data from the 6th month of 1992, right? So that's June, until the 8th month of 2010. So that's August 2010, for all the 4 variables that we are going to study. What we're doing is capturing the date information and the variables here, like as independent objects. So we don't have to call from the data set, right? If we did not do this, we will have to do something like my data $sign this, and actually in capital letters, I think it's typed, to call every time. So we will save a little bit of time actually, just by, oops, sorry, just by it's keeping them as variables here, and we will capture here the date information I'll have to double check this, to be honest, because the information is year, month, and it's QTR. So I would think that I will have to change. No, it doesn't. I'll have to double check this, but the good news is that we don't need um, to do anything with the date. In this case, we're not going to generate any plots, so you can avoid this code at all. So it's fine. Okay, let me just see what dates looks like. Yeah, it didn't capture correctly because it's not in quarterly data, it's in monthly data. So I'll have to double check how to capture that information. But don't worry, it's not going to be needed. So let's not get flustered over that. Okay, so let's estimate what ADF specifications of the 3-year rates will be used, right? So just a bit of a refresher on the procedure for the Dickey-Fuller test, the augmented Dickey-Fuller test. We will estimate a bunch of ADF variations for whatever variable we are analyzing. We compare them using AIC and BIC, and we get a selection of models. Then we go and check the residual of those models. If the residuals are not fine, we discard. If they are okay, we go with them. And then we actually perform the Dickey-Fuller test for the appropriate lags, right? Depending on the specifications that we choose before. And yeah, we check. If we reject the null hypothesis of presence of unit roots, we will stop there. If we fail to reject, then we will take first difference and go back to square one and do the first 3 steps, okay? So for the 3-year rate, let's calculate, let's perform the Dickey-Fuller estimations of, like, let's estimate the variations of the Dickey-Fuller equations. Sorry, got a little confused there. We have that function, that function already defined, so we don't need to like do any of this again. For the time series 3-year rate, and we are doing this for a maximum lags of 15, right? So you remember in the Dickey-Fuller equations that there was a summation sign, and you have delta yt minus 1 minus 2 that sequence of additions will go up to I3yt minus 15. It starts at 0 though. And we will print the list of AIC and BIC, and we will see what models are best. It's going to take a long time because it's estimating a lot of models. So it's normal to having to give R a few minutes, not actually just a few seconds for it to process all of that, all of those models and capture all that information. So when you notice that R has this blinking bar, it's time to just leave it doing this thing and just, you know, sit back and wait a little bit. Yep, it's here. So the estimates have been stored in this list, the estimates for the 3-year rates. And in that list, we have the AIC and BIC information. So we're calling from that and we're going to compare. Now, today we're going to do this comparison in different ways. Like last week, we were learning that we will find specifications that are in both lists and we'll choose them. But in this case, you can notice that the specifications are widely different. Right, the best AICs have like 7, 10, even 14 lags. With BIC, it's preferring specifications with lower lags. So there is no overlapping between these two lists. So what we are going to do is on the AIC list. So this is another way that you can subset this data. I'm just going to say this regarding like assignments, or the assignments is where you would be doing this more often. Whatever way you choose to select with AIC and BIC, will be fine as long as you justify. Okay, please don't put these are my models and that's it. Just put why. The most common criteria is, okay, I'm finding whatever models are in both lists and those are my models. Or you can say, okay, I only have one that is repeated in both lists. So I'm going to use the best in AIC and BIC in both lists and go with those three models. That's another option. Or in cases like this, you can go and say, you know what, for every list, this is the AIC list. I'm going to find the ones that the BIC is lowest, which is this, this, and this. Okay, and that's the subset I grabbed from AIC. And same for the BIC list. I'm going to see which models have the lowest AIC. So I have these, and I am putting simpler models in better position, like we have no constant, no trends 1, 2, 3, constant and trends 2 and 3, and I would also would have put one, but it seems that the AIC is quite high. So yeah, you can choose, like, as long as you justify what your choosing criteria is, it will be fine. Okay, if you decide to go with the first three in both lists, okay, but yeah, just make sure that when we read the report, we can make sense of what is your selection criteria here. Okay, because this analysis is not independent just for the specifications here. Remember, we need to check the residuals and all of that. So if the model is, if you select the model and if it's not good, it's okay. We can discard and move forward. So the next step in the Dickey Filler test that we do is capturing like those models in an adequate set and grabbing the indices for those models in order to use these indexes as the criteria to select the estimated models in the results, right? Because we want to check the residuals. So make sure for these for loops. By the way, when you're programming for loops, don't worry if you have a space here or not. It will work just as fine, but make sure you highlight it all. And actually, again, giving it a minute for it to work because it has a lot of work to do. Especially with the plots, lately my computer it's taking a long time processing plots and all of that. So look, it hasn't even shown the first plot, so it's and remember that the residual analysis is done for it's done for like with the graph and with the uh, p-value here. So let's check the graphs, but I can't get to the first one, I think. Goodness, my R lately is struggling heavily with plots. So this is the first model. They look fine. Maybe a little bit of structure here that we don't want. That's also present here. This peak seems to be quite dramatic. And if you notice here, it also seems that has a little bit of an upward trend and a little bit of a downward trend. So yeah, overall they look okay, but they do have those structures, a few of them, that would be a bit of a cause of concern. This one is not that visible in that particular trend that I was discussing. So yeah, this is just a kind of a reality check, but don't put, oh goodness, don't put a lot of importance on the graphic analysis. We just go for the p-values in here. So I prepared here. So these are the 8 models in our adequate set. Remember, we want models that we fail to reject this null hypothesis at least at 5%. Some people in the literature will be more strict and go for 10%, like values that are higher than 0.1. Other people will just say, hey, let's just agree on using 5 and that's it. So yeah, I would recommend, again, for your reports, just use 5 and you'll be okay. That's what we're doing here at least. We notice we have a few, actually a lot of p-values that are quite low. So those models cannot be used, but these two can. So make sure you keep at least 2 after this. So if we were just to have one that it's okay or none, we'll have to go back, select a different subset of models and go back to this. From all of those, I think it was 100 something models that we have. Some of them should be good. So you will not face the situation in which no specification can be used. Okay, it's always something that will work. If not in the first set of models, in the second. So it will be fine. What I would do, like in this case, if you, I don't know, if this number was too low and you only had one, what I would go is that I would go here and I would pick the, I don't know, 1, 2, 3, 4 models in here that have not been selected, and 1, 2, 3, and 4. So the remaining for BIC, and go through the process again to at least find 2 or 3 greens here. Okay, but with 2, well, we're fine. So we can go and do the Dickey-Fuller test. So we will run it. But if you noticed from the subset of specifications, we have, wait, so it's the ones that will work have 10 lags, 10 lags. So the output for the ADF test will have to expand it a little bit. So, you know, a number of lags that is higher than 10. Oops, let me delete this. All of these comments are in the solutions guide anyway, so don't worry about it. I just want to keep the R scripts just for code and little comments on what these codes do. It's just me. Okay, so let's run the ADF test for 15 lags. Remember, we get the 3 specifications, but we will only use the specifications of interest. In our case, we have, actually, let me go back to show you the 10 lags specifications that we have. One has a constant and a trend, another one has a constant and no trend. So that's why we use type 2 and type 3, and we will locate the 10th lag in here. And as you can see, we failed to reject the presence of unit roots for the 3-year rate. Okay, so it seems that it's not distinguishable from an I1 or from an integrated process, but we will need to see what's that order of integration. So what we do is take first difference and repeat the process. Okay, so I'm going to speed up here a little bit because it's going to be exactly the same thing. So I don't want to bore you too much. So again, we will estimate, but now using this diff function that we created, and we're waiting for the ADF and AIC and BIC results in there, in those results, in these estimations. And I'm actually going to wipe these plots because I'm going to be having these residual plots too often, and I don't want to be confused with the other plots that I will get, especially with how much my computer has been struggling with graphs. I don't know why. Okay, let me jump to my slideshow. So these are the AICs and BICs. So what we're going to do in here, we can find a little sample of models that are in both equations, in both lists. So we have no constant, no trends, lags 4 and 5, and a constant, no trend, lag 4 in both. So we're going to run with those 3 models. Next step, we will subset these 3 models and check the residuals. So let me do all of that in one run, and hopefully my computer won't burn down trying to calculate this. Okay, it seems that this is the last estimation in here. Errors look okay, but there's again this kind of little trends here. Like in here, it's actually a little bit maybe upwards here. So more often than not, the eye tests for the residuals are not reliable. So again, an advice for you would be put it in your report because you need to show it. But don't grab any conclusions from here. Okay, I wouldn't recommend to do that. I would just go and actually look at the p-values. So these p-values are fine. These models have good residuals, so we can do the ADF. So let's run the ADF. I expanded a little bit to 6 lakhs because we have wait, hang on. No drift, no trend for lakhs 4 and 5. So I will get this 5. I need to expand to get 6 results, right? Because it starts at 0. And I have, I think it's a 4 with drift, no trend. So it's already there. So as you can see here, sorry, here and here, and pretty much for everything, but especially for the models that we were using, we will reject the presence of unit roots. So having or taking first difference of the 3-year rates solves the problem. So the conclusion here is, and please note the wording because it's very important. I3, delta I3 is distinguishable, right, from an I1 process. But I3Y, like without the difference, is not distinguishable from an I1 process, right? We took first difference and we found that those first difference is fine. So we don't, or we can conclude that, like that we have evidence. So let me think, because this wording is kind of confusing even for me after all these years, so I don't want to mislead you there. Delta I3Y is empirically distinguishable from an I1 process, right? We found that difference in here, that distinction, but that means that the I31 variable without the difference, so in levels, is not distinguishable from an I1 process. We took one difference and that resulting time series is distinguishable from an I1. Therefore, the variable in levels is not distinguishable from an I1. Okay. I don't know if these numbers were like, this is a hypothetical. If these p-values were high and we were forced to take a second difference of these, and then we'll get something like this, then we can conclude that I3 in levels is not distinguishable from an I2 process because we needed to take 2 processes. To put it in simpler terms, it's will be integrated order 2. But that was just a hypothetical. In this case, this one will be integrated in order 1. Okay. So this is like one of the most important bits here. So please let me know if you understand or you want me to double check something. Okay, so that's for I3. Now we will repeat the process for I5. So let me jump here. The process will be the same. So we will estimate and get the AIC and BIC. Oh, what happened? Ah, still thinking, sorry. Let me wipe this because I will get more residual graphs and I don't want them to be all mixed up there. So yeah, this procedure is a bit about having patience with R while it works because it's processing a lot of data. But the procedure in itself, it's quite straightforward. So I trust that you guys will be able to follow it without much trouble. So we have our lists here. It seems that there might be some coincidences in the AIC and BIC. We could find, hang on, constant and trend for lags 2 and 3 in both. So since that's only two coincidences, let's go with those two and the first in each list. So again, this criteria for selection is quite flexible. So don't be shy of stating your own, like whatever your situation would be if you're doing this. Please be like detail that. Be careful with writing, hey, this is how I'm choosing AIC and BIC. But if you do that, I don't see any problem. Yeah, by whatever models you would choose. The important bit here is the residuals, the residual analysis. So I forgot to delete this comments in here. Don't worry about me deleting the comments. It's just like a personal preference. It will be like those comments are copied and pasted from the solution guide, so they'll be fine. So we have a few, actually 3 models. So we will get 3 graphs in here. They will look fine to me. I'm still waiting on the first one, but still, there are some little causes of concern in terms of the plot here. Again, in here it seems that it's following an upward trend after it went down here. Same in here as well. So I'll be a bit hesitant to trust these residuals. But again, we don't need to. We just need to check here what our p-values are. We will reject white noise residuals in 2 for 2 specifications. We failed to reject in another 2. So we will be a little bit cautious. So what we would do now is expanding the sample. Now adding a few other models. I think this is the AIC list. So I went back and chose some models in the AIC list that I haven't chosen and grabbed them all and redone the residual analysis. So this is what I'm doing here, adding more values to the adequate set. So it's modifying this indices, how you would do that. So modifying that and doing the check residuals to this adequate set will allow us to check all those additional specifications. So as a rule of thumb, make sure that you are that you have white noise residuals from at least 2 or 3. If you got it for 2, you can choose to go back and expand. But like if you got 3, you're pretty much good. Sorry, I had forgotten to press the button there. Okay, it's coming now. Okay, it's done. I'm not going to stop on the graphs. Again, like the only way that you would discard a model based on the graph is as if you see something dramatic. And it will be reflected in the p-value anyway. So from this point onwards, I mean, I had to note, and if you do a report, please put the residual plots. but for practical terms, I'm just going to base all of this analysis on the results on the test. So I add, so these are the extra specifications that I added. I think they are 5, 1, 2, 3, 4, 5. Yeah. So this is the additional specifications. Again, for a few of the new ones, white noise residuals are rejected, but we got a couple that are okay. So we can move forward with these 4 and do the ADF test. Again, please be careful of the structure of your models. In here, I have 2 no constant, no trend models will be this one and this one. And I have 2, like 2 greens that have a constant and a trend. So that's what I would go for type 3, type 1 and type 3 equations. Okay, so again, another thing to be careful. In here, you can notice that I will fail to reject the presence of unit roots are all 4 specifications. So, so yeah, it seems that, I mean, this result is not as conclusive because technically we will be failing to reject at 10% here. So it's not failing to reject at all significance levels, which is something like it's always a result to be concerned about, especially because of the wording that these conclusions are done, right? In here, we will say that it's not empirically distinguishable from an I1 for starters, but if you are a little bit flexible, maybe you can distinguish it from an I1 process. So the conclusion here that there is not as, black and white as we had it before. In here is a little bit grayish. So it's always a cause of concern here. It's definitely not stationary. It's definitely not I0. So, so let's do the difference, but the conclusion are going to look a little bit different than I3. Just, as a little heads up. So let's repeat. Oh yeah, and when you run the ADF test, make sure you control or account for the extra lags that you will require. Like just giving it like as this will give 5 or 6 lags as for default. Just make sure you add more because you will need it, right? I will need to estimate models that have 11 and 10, sorry, 10 and 11 lags, so I will need more. So that's why I'm go all the way up to 50. Sorry, all the way up to 12. Let's now do for the difference of I5, right? So let's check the ADF and sorry, AIC and BIC of this. Oh, actually, I did go for all, but let me stop R here because I don't want to get like too much output here at once, or my computer, it seems that's going to die. So let's get it up to the ADF, AIC and BIC selection. Okay. So we have our models. Let's see the selection. I will not, like from this point onwards, I will not stop at the selection process. I'll just give you the subset that I'm going with. You will find that when you review it, it's because the models are in both lists or either are the best in one and the other. Each of these selections have their own criteria behind, but I will encourage you to find your criteria as you like encounter these situations and roll with them. Okay, not always you'll find any overlapping between the two lists, so you have to work with it. So we'll go with these 4 models. And now off to the Dickey-Fuller test. I wish there was an option for these check residuals to do not have to actually give me the graphs, because I think that's what's keeping my computer so slow for some reason, but it's coming, I think. Okay, so we have these 4 models. P-values look okay, right? Quite high numbers, so that's good. So we will use all 4 for the Dickey-Fuller test. So again, mind the specifications. You have 3 models that do not have a constant nor a trend and go up to 6 lakhs, and one that has a constant and a trend. So you need to make sure you get at least that 6th lakh in the output. So that's why you go up to 7, right? You get the 6th one in here. And yeah, find your models. These are my subset, but as you can see, unit roots are rejected for all the specifications. So regardless of our set, that's okay. But of course, we will need to follow the process at every point. Okay. So it seems that delta I5 is distinguishable, so empirically distinguishable from an unit from an I1 process. But we cannot conclude that I5 is not distinguishable from an I1 process due to the kind of dodgy result that we got there. So make sure you just state that. Like in practical terms, I would say that I5 is an I1 process, but it's not conclusive from our results. Okay. Let me see. Okay, now let's repeat the process for 90 days. So I will go and estimate the models up to before the residuals to get AIC and BIC. So let's again give it a second for my code to work. Okay, we have our lists here. So let's selection, crossing, I believe, no, these models are not in, I think there's no overlapping here. So I think what Eric did was to go for the models, for example, in AIC that have the lowest BIC, like this, and same in here. So regardless of the criteria, these are the models that we're going to use. We have 4 models of a constant without a trend from lakhs 1 to 4, and 1 model with a constant and a trend, and 4 lakhs. So let's use these 5 and let's check the residuals. Let me try something here. Maybe that will work. I would really appreciate if it works. Yes, good. Alrighty. Let's check the again. I will not upload this R script with this plot here as false. I'll actually delete it now, because for your reports, you need the plots to put it there. Okay, so make sure you grab all that information. But for the sake of sparing my computer a little bit of suffering, I'm using that argument there. Okay, for first two specifications, the residuals are bad, but for the others, the residual seems fine. So with these three models, we can go on and do the decay filler test. I'll try to speed up because I noticed that this is like a lot of repetition and I don't want to lose you guys too early. So in my models here, I am rejecting actually the presence of unit roots at the 90-day rates. So it seems that we don't need to take first difference, right? We already got a result that will will show stationarity. So that's good. That I mean, and sorry, the conclusion here, the appropriate conclusion is that 90-day rates are empirically distinguishable from an I1. Okay, so it pretty much means that stationary as it is. That's good. That's I mean, it's not better or worse. It's just an interesting result. Now for the 180-day rates, I'm going to just show this output as I got it because again, I don't want to bore you guys too much. I'll get a subset in here. I think criteria will be, there are some models that will overlap and some models that are better in both lists. So I got this quite large subset. I have 4 models that have a constant node trend, lags from 1 to 4. 4 models that go from constant, that have a constant trend that go from 1 to 4 lags. So checking the residuals, I found that all the residuals are good, although a couple of them will be rejecting at 10%. But again, we're working with 5, we're sticking to our guns, so let's not worry too much. In terms of the specifications, remember we had models constant node trend and constant and trend, so we will keep types 2 and 3 to reflect this and locate our models, right? Lags from 1 to 4, 1 to 4. And in here, we get a result that it's contradictive, right? We get that for some specifications, we would reject, well, actually not for this, this should be red as well. And this one will be red as well, sorry about that. But at least for these 2 and 3, we are rejecting the presence of unit roots, but for these 2 and this one, we will be failing to reject. So when we got results like this, again, it's clearly not I0, right? But even if the first difference of the 180-day rates are I0, we can't conclude that this is I1. So it's a little bit of a conundrum that we find here. So we repeat the process for delta for the 180 days. We get the subset, check the residuals, so residuals are okay. So we check the ADF tests. Now remember, we have a few no constant, no trend models and constant and trend models. So we will go with types 1 and 2. We locate our models. Anyway, we reject the presence of unit roots for all of these. So delta I0 is distinguishable from an I0, I1 process, right? But we can't say that the variable in levels, so 180-day rates, are not distinguishable from an I1. So when we get this like kind of contradictory results, we need to be careful there. Okay, so now let's move on to question 2, where we're going to perform the Engle-Granger test. So in here, what we're going to do is to, like, especially because we have more than 2 variables, we have 4. So what we need to do is to run OLS using all the variables as dependent variables. So like doing all the possible combinations. We'll start with with the 3-year rate as the dependent variable, do the process, then with the 5-year rates as the dependent variable, then the 90 and then the 180. And we will obtain the residuals from that regression and check if the residuals are stationary with the ADF test. So we will repeat the process again, but for the residuals. The null hypothesis of the Engle-Granger test is that that residual series has a unit root, therefore it's not stationary, therefore the time series are not co-integrated. And I had this from a previous tutorial when we were working with Stata that we needed to be careful because the critical values from the ADF test are different than the critical values from the Engle-Granger test. But the package, I think, ETSA that we installed has a function that will allow us to like overcome that situation. So that's going to be okay. And also because I've noticed in some questions that have been brought to my attention from the quiz, is that you actually need to check the ADF test critical values and the Engle-Granger. Please note the sample size is a factor here. So I have over 200 points of data. So that's where I would use this critical value. So let me show you how we would do this. We will do a simple linear regression of I5 as the dependent variable and I3, I90, and I180 as the independent variables here. And we will capture the residuals. Then we will do the ADF test of those residuals, check the residuals of those specifications of the ADF test. And actually, let me run it up until this point with the residuals and all. In the meantime, I'm going to show you the models that I'm going to keep, which are plenty, and not to say that are all of them. I think they overlap in both lists quite heavily, so that's why our subset looks quite massive. We will go with that. The more the merrier, I think. And and note that we will use results from type 1, type 2, and type 3 equation results in the ADF test. Okay. The residuals of all of those 10 specifications look fine. And then we will go and check the Engle-Granger results. So it's still working. I forgot to turn off the plots. That's why it's taking so long. Okay, it's coming. Okay, our results are good. Like I'm going to wipe all of this, so my computer won't waste more time trying to get those plots for some reason. Now, up until this point, we will not use the ADF test command, especially because on the ADF output we don't get any critical values. Let me try to show. Oh, actually we do. Well, technically we can compare these critical values, these statistics to that critical value that I showed you, but we don't need to do that. There is a function here called coint test. We specify the dependent variable and the independent variables using cbind, and it will do it for us. So what I will do is because we have different specifications for like the 3 equations of the ADF test and the different number of lags. So we will create a matrix to store those results that is empty, and we give the appropriate names. And then with this loop, we will fill each of those rows of this matrix of results with the results for every equation of the Dickey-Fuller test and lag length. Okay, so let's run all of these, and we will get this nice table in here with the hang on one second, I always get those mixed up. Yeah, 1. So type 1, type 2, and type 3 for lags 1, 2, 3, and 4. So it's kind of the same table, but transposed, if you must, and joined together, because the previous one, the output was separated by types. But we get this result, which is quite odd, right? Because we found that for type 1 equations, and we failed to reject the presence of unit roots for that residual series, but for the other two types, we will reject. And we have specifications from our set that are in all three types. So we can't just dismiss this and get the result that we want. This result is highly inconclusive, right? So when this happens, one possible cause, and I'm going to mix this with question 3, which is interpreting these results and getting to a conclusion. The first thing to note is, remember that the 3-year rate we found evidence that is not distinguishable from an I1, right? I3, we couldn't conclude with a lot of confidence. We found that 90 days was I0, and we found that the 180 days might be I0, but we're not sure. So that condition that all the time series are in the same order cointegration is not met. So that's probably why these results are contradictive. Okay, so when results are contradictive like this, that we have many possible scenarios, like not a scenario. There's some inference that we can draw regarding the order of integration of the variables. Remember, we have a couple of there that are a little bit fuzzy. They're not clear. So when this happens, we might have that all 4 time series are I0, which is not true, right? We found that another possible cause is that at least 3 are I1 and a 4th is I0, which seems somehow likely. Or we have that 2 are I1 and 2 are I0, which also can be the case. Okay, so yeah, remember those situations. I will invite you guys to go and go, because we are not going to have a lot of time, but go through the solutions and check that discussion. There is like when results are contradictory like this, it's bad because we can't further conclude on the variables that we were having a bit of a confusion there regarding the order of cointegration, but still good stuff there to remember. Okay, so but we will have to press on, because we will repeat this process again, but with I3 as the dependent variable, then with 190, and then with 180. So it's going to take a while. But let's change the dependent variable and let's see if our inference changes. So regarding the code, what I can tell you is to make sure that I3 is the first variable here. The space here doesn't really matter. It's just me being OCD. But yeah, grabbing the residuals and checking all of that. So let me do all of these, but without the plot. So my computer will be spared of all of this suffering. And sorry, my throat's still a little bit weak, but I'm good now. So yeah. Um, Even without the plot, still taking a while. Okay, they are here. All right, so we will check different specifications for the residual series. Again, we have specifications in all three of the types, right? Type 1, type 2, and type 3. Lags from 0 to 3, 0 to 3, 0 to 1, but most likely we could have gotten up to 0 to 3, like you see here, 0, 0, 2, sorry, 1, 1. There is only a couple, maybe, but yeah, we have of three types in here. We go and check the residuals. White noise, that's good. So these are the residuals of the residual time series. That's a bit odd there, but inference is the same. And then we will go and do the Engle-Granger test. So again, this code is exactly the same. The only thing that you need to be careful with is this. Make sure I3Y is in the first term in here, okay? Oops, seems that I didn't run this. All right, we have our Engle-Granger test results. We have specifications in all three equations. Again, we get these contradictive results. So it's still pointing to that possibility. I mean, it's still reflecting that problem or that not a problem per se, technically, is that we are violating that condition that the time series should be integrated in the same order. So it's reflecting that. And yeah, those results are a bit contradictory there. So we can't, I mean, the problem with these results is that we can't either say that they are co-integrated, but nor that they are not, right? We can't conclude that for sure. So that's what makes all of this quite sad. But if you encounter such problems in your reports, make sure that you say why you can't conclude that they are correlated or co-integrated or not co-integrated, okay? If you get like all of these are 0.1, 0.01, 0.01, 0.01, that's okay. You can conclude, okay, we have evidence to say that these time series seem to be co-integrated, okay? If all of these are high numbers, then we say they are not, right? But in this case, when we get like one of each, we can't conclude for sure. So that's why I really want you guys to go home with and remember that. Now we will move to the 90 days. So again, the procedure of, again, another comment here, sorry about that. I'm gonna leave these comments in the result, in the data set that I'm going to share with you. And R script, sorry, not data set, R script. So let's do the same thing. Let's estimate the model and get up to the results. Oh, hang on. Well, let me make these plots false. Okay. Okay, the estimation has been done actually quite fast, I think. So let me share my presentation again. Wait, are we in the 90-day? Yeah, just making sure I'm displaying the right thing. In here, again, we are choosing, this seems to be a pattern now, quite odd. We're keeping a type 1, 0 to 3, type 2, 0 to 3, type 3, 0 to 1 again, but it seems that these are the specifications that are in both lists, so it's good. Checking residuals, that's so good. And then we go to the ADF test. So let me, ADF, no, sorry, Engle-Granger test. So let me produce the results again. Make sure that your variable here is 90 days, okay? And we get this table and it looks slightly different, but the results are the same. We reject no co-integration for the type ones, but we fail to reject no co-integration for types 2 and 3. So again, our result, it's a wah, wah, wah. Not good. 180 now. So we will repeat the process. Oops, right. Let me sort this option here. I should remember that. And actually, let's go all the way and get the Engle-Granger test results there. Actually, while it loads, I can show you. In here, the results, like not the results, sorry, the selected models look slightly different, but that's no problem. We still have a few of each type 1, type 2, and type 3. But instead of going from 0 to 3, now it also has a 5 like there. It's good that these things happen so you guys don't see a pattern and think that that's the case all the time, right? It's good that we can review these things case by case. Checking the residuals, all good. We can go with these models, and unfortunately, when we get to the Engle-Granger, we get that they are not good, right? The results are not conclusive. So that's again, I mean, technically, it wouldn't change the fact that the conclusion of co-integrating relations, because I mean, when we get a weird result, at least with one of the 4 combinations, it's still a matter of, it's still enough for us to say, hey, we can't conclude for sure. For concluding of co-integrating relation, all the 4 results need to be consistent. If at least one of the 4 is not consistent, it's we don't have enough evidence. And co-integrating like a significant co-integrating relation is quite a strong assumption. So we need to be careful there, okay? Finally, for question 5, we're going to test the expectations theory of the term structure of interest rates. This expectation theory states that the spread of the rates in the capital market and the spreads on the rates in the money market are stable. What does this mean? Means that when we subtract one minus the other, that resulting time series is stationary, okay? So we will go by pairs. We will go and check if the ETT holds for the capital market rates, and then we will go and see if the ETT, that expectation theory of term structure, holds for the money market. Okay, so we're going again to repeat the process, but now not for a regression, but for a subtraction of these 2 time series. So that resulting time series is what we're going to check. Again, the procedure is the same, so just going to save a little bit of time. So yeah, now our variable is 5-year minus 3-year. We can do this. This operation will be done. This this function is vectorized, meaning that it will operate on either an independent vector or an operation of a vector, if you know what I mean. If you don't feel comfortable with this, you can like say, okay, this is a resulting time series, and whatever the subtraction between these 2 terms, I'm going to call it res, and that is the time series I'm going to use. Again, that's it seems that res is something, but it's okay. And we can go on with that as well. Will not be a problem at all. But I don't want to keep these on the R scripts that I'm going to share with you because I'm not authorized to change those materials, right? So yeah, we're going to subtract checking the AFCs and BICs, and then the residuals. And with those models that we get, we will check the ADF test. So again, it's going to take a little of time. So let me just go on and show you. We will get these two tables. It seems that they are quite different. There are some similarities, but not too many. So I think what Eric did was to grabbing the best in both and a couple of coincidences. And that's the subset that he went with. Again, and I cannot stress this enough because I know this from experience that every time there is something so subjective like ASC and BIC selection, you guys tend to get a little bit tense. Don't worry, just write down how you're choosing these. Please first check for overlapping. If you don't have enough overlap models, like if you don't have at least 3, then go on and give more arguments of why more models, what models should be added to have a set of 6, maybe 8 models moving forward. Okay. And please note that we have types 2 and type 3 specifications in here. So we go on and check the residuals. Oh, sorry, this is a red as well. My bad. Let me fix that in my slides because I don't want to have that problem in the future. So yeah, we have a couple of reds. We actually have, I would say that this is a yellow. It's too close to 0.05. Technically, we are failing to reject, but oh my goodness, that's close. And the others, bit of a close call, but fine. So let's go with those 4 models. So we find them, and we find that we reject the presence of unit roots in, actually, let me see the 0. Oh no, the ones with 2 lags, they have good residuals, so we need to consider them. So yeah, this in this case, we don't, I mean, again, we have contradictory results, so we don't have enough evidence to conclude that the expectation theory holds in the capital market rates. Oh, sorry, this is misprint here as well. It's not the, sorry. It's not for the 80 days. It's for the capital market rates. Is that since all of this is recorded, this would be like up there, and yeah, it might get a bit confusing. But going back to it, we get contradictory results. That's never good. We can't say that the expectation theory holds. We can't say that it doesn't. So that's pretty much our conclusion. We don't have enough evidence to say that it holds, nor that it doesn't. Okay. We will go on. Oh, sorry. And yeah, the other specifications as well. I think the ones that we do not consider are, hang on, the 0 lags. Yeah. Sorry. 0 lags, we reject. Residuals, 0 lags, we reject. So going to my slides, technically I should not be, hang on. I should not be considering those 0 lags specifications there. So yeah, even the results that we actually work with, they have contradictory results, so that's no good. But let's try our luck with the 180 days and 90-day spreads. So just again, going through all of these, we have models in the three types. We subset that, we check the residuals. Residuals look fine, all of them. So we can go on and find all of them. And look, this is a good result. Even if this one will leave us to conclude that fail to reject, this type 3 with 0 lags is not in our subset, so we don't worry about that. And for all the others, we are rejecting. So oops, again, sorry, just keeping nice slides also for the video for you guys. So you guys know what I'm talking about when you check this recording. Yeah, in this case, we will reject that presence of unit roots in that residual time series. Therefore, we can conclude that the expectation theory holds for the money market, capital market rates. Okay. Yeah, capital market rates. Actually, and I just noticed that, sorry, here is the here it's the 180 days and 90 days, but just you know, just stuff to solve real quick. So yeah, we found that yeah, all residuals are okay. So yeah, we have enough evidence at least to say that it holds for the capital market rates. So that's as far as we can go in terms of this. Please remember please remember the wording of these conclusions, right? In this case, for example, the spread of the money market rates is not I0, but we can conclude that the spread in the capital market is I0. Therefore, the ETT holds for the capital market. So that's good. I mean, it's a result, right? So yeah, I'm not going to bring any more confusion into your heads for now. I'll leave you guys, you know, process this. Again, the recording will be up there for as long as YouTube allows me to. So don't worry, you can go back and recheck. Please remember, again, I cannot stress this enough, the wording of the conclusions, it has to be appropriate. We are supposed to check that. Don't lose marks in a silly matter for that. And yeah, that's all I'm going to do today. So I'm going to stop this now. Please don't forget to check the quiz and the first assignment. Do it with plenty of time so you don't are short on time. You know, closer to the date, because if you come to consultation closer to the date, trust me, you are going to have problems finding a tutor that will help you, okay? Or have the time to help you. We always want to help you, but we are, you know, our time is limited as well. All right, that's all. And thank you so much, you guys. Enjoy your weekend.